So we are starting chapter 2 today. This first section is pretty fast. Most of it is pretty intuitive, other than the very last part will be where it'll be something a little bit new for you guys, but it's actually not anything very difficult. So here we go. The first part here, you probably know. What is a percentile? Have you guys heard of a percentile before? Yeah, you have. When you get your SAT, ACT scores, they always tell you, here's your score, and you are in this percentile. What does that mean?
That percentage of participants.
Yeah, so that means you did better than. Now, I will say the statistical world usually says that a percentile is what percent you did better than. 4 years ago, for whatever reason, College Board updated their description of percentile, and they did include equal to. So for our purposes, it is the percent that you did better than or equal to. Okay. So for our purposes, it's going to be greater than or equal to. So a percentile is the percent that is less than or equal to a less than or equal to the value in the distribution. So we're talking about a particular value in a distribution, and the percentile is the percent that is less than or equal to that particular value in that distribution. So, is your percentile equivalent to what you got on the test? No. So you can get a 50 on the test and be in the 90th percentile. What does that mean about the test? It did not go well, right? If you got a 50 and you did better than or equal to 90% of people, that means that only 10% got more than a 50, okay? That would be sad, right? You can get a 90 on a test and be at the 90th percentile. So they can be the same, but they're not always the same. So a student percentile is not the same as the percent score. A student's percentile is not the same as their percent score. All right, so let's look at an example here. First of all, what kind of graph is this? Stem and leaf plot or stem plot, either one is totally fine. Did they split stems here? Yes, they did. Do you notice that there is not any on that first 6? Why not? There's nothing from 60 to 64. So there's nothing there. Did they provide a key?
Yeah.
Perfect. All right. This is the data that shows the number of wins for each of the 30 Major League Baseball teams in 2016. We're going to calculate and interpret the percentile for the Detroit Tigers, who had 86 wins, and the New York Yankees, who had 103 wins. So here we go. 86. Detroit Tigers had 86 wins. Can you find 86 in the data? Any problems with that? Oh my gosh, there's 3 of them. What do we do? Which one of those is the Detroit Tigers?
Does it matter?
Does it matter?
Does it? No.
I am trying to find what percent is less than or equal to the Detroit Tigers. And whether they are the first one or the last one, 86 is equal to 86, which is equal to 86. So it doesn't really matter. So, very good, Aaron. So we need to find out how many of the 30 teams had less than or equal to 86. Make sure you're only counting the leaves, not the stems.
I'm 100%.
I'm 105%. No.
So that's what we're counting. That's how many are.
Bottom ones and then subtract by 13. Or subtract by 30, wouldn't it be the same?
So you,
Count the 86.
No, you count the 86.
No.
if you're doing less than or equal to, so we're counting the bottom ones, and there's 20 that are 86 or less, and there's 10 that are 80 or higher than 86. So, what percentile is that then?
67.
All right.
Wait, do we count
So, 20, yes, less than or equal to. So 20 out of 30 is 66.66666. So we're going to round this to the 67th percentile. So what does that mean about the Detroit Tigers?
They scored less than or greater than or equal to.
They won more than or equal to Yeah, that was a weird sentence. They had a number of wins that was more than or equal to 67% of the teams. Okay, so the Tigers had a number of wins that was greater than or equal to 67% of teams. Alrighty, the good old New York Yankees. They won 103 games. And can you find them in the data?
The only one.
They're at the top. So,
Nobody.
what percent did they do better than or equal to?
99.99.
100%. Now, this is where AP statistics deviates from real statistics. In real life, you will never see someone say anything about the 100th percentile. But in AP statistics, 4 years ago, the College Board updated this definition and included the equal to. So, if you had been in my class 5 years ago, we would not have said the 100th percentile. So this is, though, now considered the 100th percentile. Okay? So the Yankees had a number of wins that was greater than or equal to,
Just kind of redundant.
it feels very redundant, 100% of teams. Yep, they did better than or equal to themselves. Okay. We'll go with it. I will say for the majority of data, if you're talking about percentile, you're usually talking about a very, very large set of data, like the amount of people that take an SAT or an ACT score or test. And so usually you're not going to find the person that scored the highest. Is usually not the one you're talking about. All right, cool. Questions, comments, concerns about percentiles? Now we're going to go backwards. The number of wins for the Texas Rangers is at the 90th percentile. Interpret this value in context of the problem and how many wins did the Rangers have? So what does this mean? This means the Rangers did better than or equal to 90% of the 30 teams. So they did better than or equal to 90% of those 30 teams. So in that list of 30 teams, they are at the data value that cuts off the lower 90%. So which number is them?
94.
How'd you get 94?
30 times 0.9.
All right, so if I know that the Rangers are at the 90th percentile, then that means if I line up all the data, 30 pieces of data, and I say, okay, well, what's 90% of 30? 90% of 30 is 27. So that means that the Rangers are at the 27th data value. And so I can count either from the bottom or I can go backwards from the top. And I'm finding the 27th data value, which is in fact 94. So 90% of 30 equals 27. So the Rangers are at the 27th data value, which is 94 wins. Does that make sense? Did I hear no?
Yeah, that would be me. How do you get 27?
90% of 30. So if I do 0.9 times 30, so 9 times 3 is 27. So
How did you get 90
So then I went to my stem plot and I was like, okay, this is 1, 2, 3, 4, 5, 6, 7, 8, and I counted up, and then this is the 27th data value. You can also go backwards if you want. This is the 30th data value. This is the 29th, 28th, 27th. So it's like, what position is it in the data? It's the 27th position. It's the, yeah, there you go. All right, cool. The next thing we're going to talk about, guys, we're going to talk about a cumulative relative frequency graph. That sounds like a scary graph, but actually it's not that bad. It's literally something you've probably seen before. What does it mean to accumulate something?
Add it all
To
together.
add it up. What does it mean for relative? What does relative mean?
When it's pertaining to a specific area.
So kind of part of the whole or part of the area, right? Okay. Percentage. We want to think percentage when we see relative. So I'm going to accumulate the percentage. And what does frequency mean? How often something happens. I'm going to accumulate, I'm going to add up the percentage of frequency for this data, or how often this data happens. So this is the distribution showing the lengths of phone calls made from the mathematics department at UNT last month. So here's their phone calls. If you notice, the graph starts at 0 because I have 0 data. And then I continue to accumulate the data as I go until I get up to 100% of the data at the very end. The call length is here at the bottom. And then the difference between one section and the next is how many calls were added at that call length. So anytime the graph goes up means that there was some data added to the distribution. Why is this flat from 20 to 25?
No call for it.
There's no calls added there. So that means that for whatever reason, there were no calls that lasted from like 20 to 27 minutes. I don't know why. They're either short calls or longer calls. It's somewhere like that, okay? All right, a phone call lasting 30 minutes is at what percentile? How are you going to do that?
You're going to draw a line.
Yep, we're going to basically go to the graph, look at 30 minutes, go up to the graph, and then go over to my y-axis and ish.
65.
65-ish? Do we agree with Danny? Sure. Why not? So this is about the 65th percentile. What does that mean about a 30-minute call?
It's longer than 65% of the other calls.
Oh, you were so close.
Or equal.
A 30-minute call is longer than or equal to 65% of all calls.
5 years ago, I would have.
5 years ago, that would have been perfect answer. You're absolutely correct. Thank you, College Board, for ruining my life. I mean, no, just kidding. Perfect. Any questions on that one? All right, here we go. Part B. Moving on, because this is too easy. Let's speed up a little. What is the 25th percentile of this distribution? What is the call length at the 25th percentile?
13 minutes.
All right, Danny says 13 minutes. Does anyone agree?
I guess, yeah.
No, 12.
Wait,
Definitely 12.
12?
Definitely 12.
Oh, yeah,
No, that actually is 12. We're putting 13.
I've been going with 13 for the last 8 years, so I guess I'm going to stick with it. I mean, 12 I would have given
But
you full
you've done
credit
this
on the
for 8
test.
years in a row.
Yeah.
This like you just do the same thing.
I've been using the
Zero
same.
doesn't change.
No, it's even. All right, you guys. Hey, whoa! What is another name for the 25th percentile?
The first quartile.
The first quartile, quartile 1. So that means that you guys just found Q1.
We want us to find the 5.
I now want you to find the IQR. How do you find the IQR?
Find Q3 and subtract
75%.
Q3 minus Q1. And how do you find Q3?
Do you find the 75%?
It's the 75th percentile.
Yeah, 33.
And about where would you say the Q3 is?
32.
33, so it ends up being 20.
Definitely 30.
I think that easy math is good, so we'll go with 33 to go with our 13, which makes it just 20. I promise you guys, if you tell me on a test it's 12 and 32, or 12 and 33, or 13 and 32, I promise you you'll get full credit. Yeah, that's a good point.
Can you do 20 times 1.5, bro?
All right, interpret this in context of the problem. What does IQR stand for? And what does that mean?
It means the range in between the quartiles.
The range of the middle 50% of data is 20 minutes.
Stuff is easy, but at the same time.
What do you mean this is the hardest thing?
Alrighty, let's look at the next part. Next part says, where's the original graph the steepest? What would you guys say?
Well, like 10 to 20 range.
I'd say 10 to.
Let's go.
Yeah, somewhere around 10 to 20 minutes. Again, there's some wiggle room there. And what does that mean? Why did it go up so fast right there?
There's so many of them.
There's a lot of calls being added right there. So again, steeper graph means that I'm adding a lot of data there. I'm accumulating a lot of data. Flat means no data is being added. There were no calls from 20 to 25 minutes for some reason. All right, so a steep graph means there are a lot of calls lasting this length. Okay, here is a difficult question. Is a 35-minute call unusually long? Think about that, look at your data, and make a decision.
Definitely not.
Is a 35-minute, based on this data, a 35-minute to the UNT math department, is that unusually long?
Because look how many are in there. Like, look how steep it is. That's not bad. Look how steep it is at 35.
30.
Yeah, no, it's not.
Oh, wait, no. Yeah, you're right. It's not.
Because like, yeah, because like, it's like 36.
No, it's not. And the
I feel like that's-
outlier is 60.
I don't think it's a problem. Oh, that's right.
1.5 times 30 plus.
Well, I'll just be completely wrong though, and it'd be like, actually, it's the most usually long number in this list. It's just like problems and whatever.
All right. How many of you think that that is unusually large? How many of you think it is not unusually large? Okay.
How many of us are wrong?
Tell me, Ryan, why you think that that is unusually large.
Because it's outside of Q3.
Okay. And for those of you who say it's not, tell me why you don't think it is.
Because it's not an
It's on
outlier.
a slope.
Okay.
Yeah, it's
Okay.
on the slope thing.
So it's not an official outlier. If you do the 1.5 IQR rule, Remember the 1.5 IQR rule?
Oh, yeah, I do.
So the 1.5 IQR rule would mean that it's not technically an outlier, okay? However, what percentile is it at?
95.
It's at the 90, 93rd-ish. It's at the 90th percentile, which means there's only 10% of the data that's more than that. And so this is an example of you could actually argue this either way as long as you give statistical reasoning. Ryan is correct, and so are the rest of you. So you can say it either way as long as you give a statistical basis for your answer. So if you want to say no because it's not an official outlier from the 1.5 IQR rule, perfect. If you want to say this is longer than 90% of calls, so that is unusual, great. You get to decide which one you think is the best. I'm not writing any of them down. I'm not swaying your opinion. I ain't skewing this data.
Wait, so saying
Ooh.
a 35-minute call is longer than or equal to 95% is saying it is a...
That's kind of unusual. I mean, if something is happening,
Right off.
if something is happening and it's longer than 95% of other things, that's kind of unusual. But it's not
Switch my
so unusual to be an outlier.
I just made it. It's unusually long. It's usually 10%.
Yeah, it's in the top 10%.
Yeah,
If you're in the top 10%, are you special?
No.
Yeah.
Nobody's special.
We're all special. All right. So again, I just want you guys to see that sometimes you can kind of argue your own opinion as long as you use statistical backing. Okay? So statistically speaking, you should really never get anything wrong. Right. All right, let's talk about Macy and Brody. Yes, ma'am.
Macy Brody.
You have to justify, can you just say because it's not an outlier, or do you have to put it in
You could say because it's not an outlier from the 1.5 outlier rule. Or 1.5 IQR rule, sorry. All right, we're going to talk about Macy and Brody. Macy is a 3-year-old female. She is 100 centimeters tall. Brody is her 12-year-old brother, and he is 158 centimeters tall.
Want to be my B-reel?
Yeah. So you guys can look at this data very easily and see who's taller, y'all. I got a 100 centimeter tall Macy, and I got a 158 centimeter tall Brody. Who's taller? Brody, obviously. Okay, but wait, there's more. Who is taller relatively speaking? So relative to kids of their own age, who is taller?
Brody's actually a bit.
So here's what we have. According to the Center of Disease Control Prevention, the height of 3-year-old females have a mean of 94.5 centimeters and a standard deviation of 4. The mean height of 12-year-old males is 149 centimeters with a standard deviation of 8. So I now know what kids their age average and what their standard deviation is. And so let's look at Macy for a second. Macy is 100 centimeters tall. Now, kids that are 3 years old, female, similar to her, they have an average height of 94.5, give or take 4 centimeters on average. So anywhere up to 98.5 and down to 90.5. Where's Macy?
Way above.
Macy is above that standard deviation. So, guys, not only is she above average, she is more than 1 standard deviation above average. What about her brother, Brody? Brody is 158 centimeters tall. 12-year-old males are 149 centimeters, give or take 8 centimeters. So their standard deviation is double that of the 3-year-old females. Why is that, do you think?
Because it's
Yeah, So when you start getting older, your heights start changing for all different kinds of reasons. Up to about 6-7 years old, everybody's kind of pretty close to the same height. And then whoosh, genetics start to come in, gender starts to come in, all of the different things. So is Brody outside of the average? Oh my gosh, you guys.
Yeah, I feel like this guy knows.
Who is more outside of average?
Because she's one standard deviation. Or she's two, but he's one.
So is she 2?
Oh yeah, she's 1.5. He's 2. Or no, he's 1. I mean, that's what I mean.
So they're both more than 1 standard deviation. So here's what we're going to do, guys. We're going to learn how to standardize their scores. All right? This is probably one of the most basic things in statistics is how to standardize a score or a scale. So it's called a Z-score. We're going to standardize using a Z-score. There is a formula, and it is not on the formula chart. Here it is. Yes, I have drop forms up here. The Z-score equals the value, so that would be like the value of the individual, so that would be like Macy or Brody's height, minus the mean of the distribution that they belong to, divided by the standard deviation of the distribution they belong to. It's not that difficult of a formula. You take their value, you subtract their mean, and you divide by their standard deviation. Now, this is how I can standardize any distribution and put it onto a standard Z-score distribution. Then I can compare them to each other. So once I standardize Macy and Brody's score, I can then compare and see who really is further above. How do I interpret this? The Z-score tells how far and in which direction the value is from the mean in standard units.
So if it was like negative and positive, is that what it means by restriction?
Absolutely. Negative and positive tells me whether it is above average. Negative would be below average. Could you get a Z-score of 0? How?
If it's equal to the mean.
If the value is equal to the mean. If Macy is 94.5 centimeters tall, she is exactly the same as the mean of the distribution. She would have a Z-score of 0. All right, do you guys think Z-scores have units attached to them, like centimeters or whatever?
No.
Why not?
Because it's not based on the unit anymore.
Perfect. It is a standardized score. It is a standardized value. That is the statistical reason. Let me show you mathematically how that would work. Let's just say we had 100 centimeters minus 90 centimeters divided by 5 centimeters. Let's see how this works out unit-wise. What is 100 centimeters minus 90 centimeters? 10 centimeters divided by 5 centimeters? That is only 2. Why? What happens to the centimeters?
Because you're dividing centimeter by centimeter.
I'm taking centimeters divided by centimeters and I cancels them out. So the units get canceled out every time I use this formula, hence the standardization. Okay? All right. What does the sign mean? So we've kind of already alluded to it. The sign of the Z-score tells you whether it's above, below, or equal to. So a positive Z-score means that the value is above the mean. A negative Z-score means that the value is below the mean. And a 0 z-score means that the value equals the mean. The bigger the z-score, the further away from the mean we have gone. So if you have a z-score, for example, you have a z-score of 3.2. That means that the value was 3.2 standard units above average. If you have a z-score of negative 0.1, what's that mean?
Negative 0.1 below the mean.
It's 0.1 below the mean. So was the value far from the mean?
No.
No, it was pretty close, actually. But it was barely below, okay? Now, you guys are going to get very used to seeing z-scores, and usually our z-scores are between 0 and 4, but you can get z-scores of 6, 7, 8. Those are those, like, really big-time outliers, really far away from the rest of the data. All right, you guys, so let's finally answer this question for real, mathematically speaking. Who is truly taller relative to each to their own, Macy or Brody? Macy's z-score, we're going to take her value, we're going to subtract her mean, and we're going to divide by her standard deviation. So, how tall is Macy? 100 centimeters. And what is the mean of Macy's distribution?
945.
And what is the standard deviation of Macy's distribution? And so, what is Macy's z-score? 1.375. This means Macy is 1.375 standard units above average. We knew she was already more than 1. She's just this extra amount, 0.375. What about her good buddy Brody? Maybe they're not buddies, I don't know. Maybe they don't even like each other. All right, so what is Brody's z-score? What is Brody's value?
158.
158. What is the mean of Brody's distribution?
149.
And what is the standard deviation of Brody's distribution? And what is Brody's z-score?
1.125.
1.125. Ladies and gentlemen, who is taller, relatively speaking? Macy. I will tell you guys, if you put Macy and Brody standing at the front of the room and you go, look guys, Macy's taller, people are going to think you're crazy. But you would say Macy is taller, relatively speaking, and then you would be covering the truth. So Macy is actually the taller one. What questions do you guys have about z-scores? Cool.